Hello everyone and welcome to my webinar session, Solutions for Industries, Protection, Drivers and Benefits. My name is Rodrigo Braga and I'm an electrical engineer working as technical sales consultant for energy automation systems at Siemens Smart Infrastructure Digital Grid. With expertise in field automation, during the last years I have been involved in several projects worldwide, working closely with distribution system operators, DSOs, municipalities and industries. Today I would like to talk about the relevance of the so-called field level in electrical infrastructures applied to industrial environments, namely the different application cases supported by protection relays and their main advantages, especially if we understand that their main objective is to secure and protect the power supply of the industrial process. So when looking at the industrial process, how to protect and secure power supply? First, let's have a look into main drivers. Transparency for higher system availability, meaning fast information for operator on fault type and location. Personal and operational safety. Here it is important to notice that the power failures can affect the safety of personnel and material, leading to costly downtimes and injuries. Protection of critical loads from power interruptions. Well, that can be achieved through automated response to failures of critical processes with load shedding or self-healing schemas, for instance. Improved power quality for network reliability and asset protection, a very relevant aspect when it comes to the life cycle of existing devices. And finally, optimization of power usage to avoid overload scenarios, a critical topic that implies automatic generation control to ensure sufficient power reserves. Understanding the main drivers, let's take a look now into the typical architecture and main components of the industrial system. As described here in the picture, in an industrial facility, there are two worlds. The first is the DCS, Distributed Control Center, which is responsible for the main processes within the plant. Example, control of motors, pumps, compressors, etc. But when it comes to the electrical energy, to enable the reliable operation of the facility, we need the EPMS, Electrical Power Management System. As you may conclude, electrical switchgears and protection relays belong to the right side of the picture. There are several reasons for this philosophy. Example, IEC 61850 is a state-of-the-art communication protocol for protection relays, but the DCS world does not really use this protocol. Besides, there are additional requirements like 1 millisecond time-stamping resolution, fault record transmission for proper root cause analysis, or harmonic measurement, which traditionally cannot be solved by the DCS. When dealing with critical electrical consumers that have a significant impact on the overall operation, it might be important to link those loads directly to the electrical control system. If we look now in more detail at the system architecture, we see the different levels of the DCS and EPMS. Looking at the EPMS, we see three different levels: field level addressing protections and power meters, station level, where substation controllers and local HMIs are installed, and SCADA level, running the electrical control center. So during the next minutes, we will be focusing on the relevance of the so-called field level in electrical infrastructures applied to industrial environments, namely the different application cases supported by protection relays and their main advantages in the context of critical operation. So let's talk about the main application cases that protection relays can address on field level. Well, as said before, a big challenge for the industrial operator is a fault in the electrical infrastructure that may injure people or damage high investment assets. Protection devices are the first line of defense and safety when it comes to the possibility of isolating faults selectively within milliseconds, protecting therefore human life and assets from damage, and preventing also the overload of primary equipment. Siemens offers in this market two families of protection devices, Cyprotect and Railroll, running state-of-the-art communication standards such as IEC 61850 that meet the demanding requirements of modern industrial operation. Still on the topic of safety, if we look into an industrial plant, immediately we will see a considerable number of medium voltage switchgears. Having these primary equipments around also brings some additional risks. First of all, to the persons which have to operate them. In order to avoid that, we have the arc flash detection. In one model of the protection relay, Cyprotec 5, we can connect 3-point or line sensors, and in one device we can have up to 5 modules. That means a total of 15 sensors can be connected, sensing the different switchgear compartments, being the busbar, breaker, or cable connection compartment. The protection in itself is very fast, clearing a fault in 3-4 milliseconds. Well, the next slide brings us a very interesting concept in cases where the plant runs with multiple medium voltage feeders supplying medium and low voltage loads. If we consider the traditional way of implementing a protection relay, normally we have one relay for feeder, and then the CTs, current transformers, and VTs, voltage transformers, from this feeder being wired to this protection relay. Now, with one single device, we can protect up to 9 feeders at a time. Imagine for a second the situation of having 5 feeders to protect, and redundant protection is also required. In a normal case, you would be considering 10 devices. With this new feature, instead of having 10 devices that have also to be engineered and tested, you need only 2 protection relays to secure the 5 feeders in a redundant way, generating therefore significant savings in terms of the number of devices required. But redundancy is not limited to the protection itself. Network redundancy is also a very relevant topic when it comes to the deployment of mission-critical applications such as load shedding or generation control. The use of IEC 61850 as a state-of-the-art standard in substations often combines the traditional SCADA requirements of reporting and control along with protection signaling for blocking and permissive signals. This protection signaling will use goose messaging, which can be published over the same SCADA network. As these goose messages are mission critical, a simple ring with RSTP is not sufficient and can also become too slow for data exchange. Dual redundant LANs require redundant goose messages carrying the same data, which is, I would say, not an ideal situation and makes it also very complex from the engineering point of view. The solution for network redundancy is to use one of the high availability networks of IEC 62439-3. Either PRP or HSR is sufficient depending on the application requirements, and both are supported by Siemens protection relays. A big step towards digitalization in this domain of field-level applications is our concept of a digital twin protection. And the benefits for the industrial operators and maintenance teams are clear. The Cyprotec digital twin is a real-time digital replica of a physical Cyprotec 5 device, including interfaces, functionality, and algorithms. The new innovative cloud-based Cyprotec digital twin offers comprehensive tests of your Cyprotec 5 protection devices as part of the energy automation system with high performance, security, and, most important, I would say, availability 24/7 from everywhere without any hardware. Only 3 steps are required. 1. Upload your engineering data in your automated test cases. 2. Simulate and test your energy automation system in the cloud. 3. Get test reports of your engineered system. No need to adapt customer configuration on available lab devices. Debugging online CFC logics, for example, becomes possible for more efficient engineering, or reduce travel costs with less on-site commissioning. As simple as that. Talking about power quality in industrial plants, you will find very often motors that are speed controlled. Based on our experience, variable speed drives are the largest possible source of harmonic generation. Modern speed drives use a rectifier to create DC voltage. This DC voltage feeds an inverter that can generate variable frequencies. According to the generated frequency, an asynchronous motor turns. If you take an oscilloscope to measure the current draw of one phase, then you will see the red wave on the right-hand side. The problem is that such continuous periodic signals do not only contain the fundamental frequency, example the 50 Hz, but also many other so-called harmonic waves. This means sine waves with multiples of the fundamental frequency. So if we take a look into this slide, we see that the main impact of harmonics is related to generation of additional heat. This additional heat mainly influences the lifespan of the isolation of wires, meaning that the total lifespan of generators, motors and transformers can be reduced. For motors, the counter torque does not really influence the efficiency of the motor, but it leads to vibrations, and these can lead to a reduced lifespan of the bearings. So to avoid harmonics, filters consisting of capacitors and chokes are mainly used. But the problem is that sometimes such filters or the inverters, they can become defective, and then the local grid faces unnoticed harmonics. The good news are that with embedded power quality functions, we are currently using the Cyprotect 5 relays to run additionally harmonic detection function at the key points of the electrical infrastructure. With that, we can recognize such problems before major damages occur. Finally, we have mentioned also the possibility to deploy intelligent automation on field level. In fact, with the most advanced IEDs, Siemens protection devices currently offer fully decentralized architectures for critical operations, especially relevant in those scenarios where critical loads are supplied by different medium voltage, low voltage stations. Interconnected in a ring structure to the primary in-feed station, the so-called self-healing application can minimize the impact of power outages on those loop structures as described on the picture. Once the fault occurs, the intelligent devices will immediately locate it, supported by the multicast of IEC 61850 GOOS messages. Once located, the devices will immediately operate the breakers to isolate the faulty section, restoring, therefore, power to the remaining areas of the plant without any human or SCADA intervention. And all done in a blink of an eye. Well, as my presentation is coming to an end, I would like to briefly highlight main points of our session today. Protection is a key element on the electrical system of an industrial plant. It prevents power outages, protects people and assets from damage, supports power quality for improved operation and system stability, and it can also be used to deploy decentralized system architectures for mission-critical operation. Thank you very much for your attention.